Right. Right. That's so good. Okay, let's get started, please. Time is going. You owe me 13 more seconds.
Of what?
We make that 14. All right. Here's our calendar for the last couple weeks of school. First lab from yesterday. Lauren,
We did a lot.
here. It's information that you'll need to finish up your packet. Okay. So, today, what I wanted to do is I wanted to revisit the topic of torque, which we actually covered way back last Tuesday, which I know seems like ages ago. So we'll review that stuff. And then we'll get into some problems dealing with torque, mostly conceptual problems, but there is one calculation problem that I would like to do just to see how it all fits together and what we're looking for, et cetera, et cetera, et cetera. I won't see you tomorrow. Then on Friday, we'll probably review torque a little bit more and then get into rotational equilibrium and what that means and where we go from there. Yes, but
Would you like to have a party on the 27th?
I wasn't really planning on it, but you know. So I usually have something that
I'll bring Joe and I.
I mean, yeah, I have something interesting planned for that test.
Ooh.
What you got interesting?
I think interesting. So,
Well, that's around.
it's like a pre-exam kind of. You know.
How is that interesting?
He gets to do whatever he wants. This is cool.
I can look at all the interesting things I want on the internet while you guys take your test. So.
Wait.
Anyway.
If we have to take the final, you guys have to make us a little.
I'll forget that.
All right. Is it just the
Is it like an
Just seconds.
That's
So, then next week. City. What is it like? This is the one.
Well, we have a parade that you all can go to. See
The next Monday we have school.
Well, next Monday.
All right. Then
I don't know how many people are going to be here next Monday.
I'm sick. Then next week we got a couple more things we need to cover. We'll take rotational equilibrium. We'll cover that. We're probably looking at quest/quiz somewhere here-ish. Okay. Meaning we'll probably go like we did for the gravitation test, something like that.
Open note.
Yeah, it'll probably be open notes. So. And then, so I'm thinking probably because Monday is going to be pretty sparse, we're probably looking at somewhere probably around Thursday, I would say. And then, yeah, no block next week. And then Friday, senior's last day.
Aww.
So,
Bummer.
what? I know, it is. Like, look.
If you have anything in the school, the month of the calendar.
The block, they're all the way down in the
When's your actual life?
My actual last day is right here. Thursday the 10th. Thursday the 9th.
Boom, snack all time.
All right.
Any crazy plans for this vacation?
Wow. We get like a week early. You're eating into my 40 minutes and 7 seconds.
I am.
So,
And you pointed that out.
Sorry.
Well,
that's true. Although less that you have seen me all have questions.
is it gonna like beep when it's done?
It does, but I turned off the speaker because when the speaker's on, the microphone's in, we get feedback.
How are we supposed to know when are we going to get periodic checkups?
Basically, I'm finishing the things I want to finish.
Does the
Which-
timer just
which-
check?
It doesn't really matter. It's all null and void now because we've wasted like 3 of the 40 minutes and 7 seconds. So,
They've all been legit questions, though.
yes, we've basically done 1 minute and 7 seconds worth of work. So, and that consisted of looking at the calendar. So, all right.
At 15, it should be done. Okay.
All right. On Tuesday of last week, we introduced this idea of torque, and we talked about that most of the year we've looked at motion, or at least one kind of motion, but really there's multiple kinds of motion that we talk about. I think we looked at this picture last Tuesday of the hammer as it was flying through the air. Okay. Head of the hammer, handle of the hammer, we throw it, it twists through the air, but as it twists through the air, we see that it also follows a parabolic path. just like any other projectile that we studied up until this point. It's still going to follow a projectile path, but as it's following that projectile path, it's also going to rotate. So we spent a lot of time talking about changes in translational motion, the forces that cause something to speed up or slow down or go in a curved path or whatever it is. But what we wanted to talk about now is changes in rotational motion. What causes things to spin faster, spin slower, not spin at all, things like that. Okay? Good there? So, there it is. So, torque. Torque defined it as a change in rotational motion, or causing a change in rotational motion, or it causes angular acceleration. In that way, we sometimes refer to it as the rotational equivalent of force, because force causes changes in translational motion. It causes things to speed up or slow down or change direction. All those things we call acceleration. This causes a change as well, but it causes a change in angular motion. Speed up, slow down, how fast it's spinning. Okay? Torque depends on two things. It depends on a force, but it also depends on a distance component. And we'll talk about those here in just a second. Okay? Good here? Mm-hmm. You're allowed to say no.
No, I haven't clear yet, yeah.
No, you just rolled your eyes.
Are we allowed to ask you questions while...
Sure.
What we're asking?
Oh, well. I went on Windseeker. No, not Windseeker, sorry. Skyhawk.
Gonna go in?
I've been to
Never go to the mini.
All right. So. Now I know.
No, she's
Unit is meters.
All right. Talk about that.
sorry.
There's our formula for torque. This lowercase tau, we use that to represent torque. Like I said, torque depends on two things, depends on the force and the distance, but the fact that we're including the sine theta in here means that we're also going to deal with components, and we'll talk about how the components get entered into this in just a second. Okay? Basically, by including the sine theta in the formula, we're always getting the correct component, the one that we need, the one that actually causes the torque. So, T stands, or tau stands for torque, F stands for force applied, D stands for the lever arm, the distance from the center to the point where the force is applied. If we're talking about a solid object, we said a lot of times this D value, the lever arm, is just the radius of that object. But if we have something that's not solid, something like this, right, we can apply that force at different places from the center and cause different amounts of torque, cause different amounts of angular acceleration. Does that make sense? I think we did this demonstration last Tuesday, correct? Mm-hmm. Okay. All right, and then theta, we said was the angle between the applied force and the lever arm. Okay. So I think we looked at this picture. Oh, unit, newtons times meters. And I think this is where we left off, right? I don't think we got much farther than this. Okay. All right.
Wait, I don't, so D is the lever arm.
D we refer to as the lever arm, which is just that
Not
distance.
like,
Good.
it's just a fancy name for the distance.
Basically, fancy name
So
for
why
the
is it
distance.
just weird?
Yeah. Just like, we come up with weird things to represent. Physics is kind of famous for that.
Yeah, it just explaining.
All right. So picture. Here is a rotational motion. Here is a nut with a wrench attached to it. Okay. And it could be a screw, whatever. Okay. So here's the force that's being applied. I'll go here. In this case, the length of the wrench is going to be D, the lever arm, because that's how far away we're applying the force, as long as we put our hand on the very end of the wrench. If we hold the wrench in the middle, then that D value, that lever arm, is going to be somewhat shorter. Okay? And then, this is theta, the angle between the force and the lever arm. So in this case here, we're greater than 180 degrees. But here, we have another theta, less than 180 degrees, but you're going to get the same answer. Yes, Bruce?
What's the red line again?
The red line is the actual force that we're applying. So that's how hard you're pushing or pulling on the wrench. Okay? Good there?
Yeah.
Forces and torque. First, not all forces are going to produce torque. Okay? Only forces or components of forces that are perpendicular to the lever arm are actually going to produce torque. Forces parallel to the lever arm, or forces that pass through the middle of rotation, don't cause any torque. For example, if I take this bike wheel, right, I can apply a force at point B, cause some spinning. Right? I can apply a force at point A and cause some spinning. Okay? I think we did that demonstration in class, right?
Tyler did it.
Tyler, do you remember what one was easier? Do you want to try it again? I think it was, yeah. Try it again. Real fast. So go B, okay, and then A. Definitely A.
Yeah.
Okay. But there is a way that we can push on this wheel, apply a force to it, and cause no torque whatsoever. Right? Right? I apply a force to the edge of the wheel like this. Okay? I'm applying a force, right? Go back to our torque formula. I'm applying a force. There is a lever arm, the distance from the center of rotation, but is any torque being caused? Is there any spinning, any change in the rotational motion? No. Okay? Because that force that I apply to the outer edge of the wheel, if we draw the line, if we draw the arrow, it's going to run right into the center of the wheel. And forces that pass through the center don't result in any torque. No torque is being created from them. Okay? Like this. If I take this wrench and I apply the force this way, right? If I push on the handle of the wrench towards the nut, right, or towards the screw, whatever, or bolt or whatever it is, okay? Nothing's going to happen. No spinning is going to happen. Can I cause translational motion? Yeah, I can cause the bolt to move if I push hard enough, okay? But no spinning is going to happen. So if we look at this force, right, here's that force from before, but it's got some components, right? This component, if we look at the picture, the vertical component, where does it pass through? We draw the line. It goes through the center. This one doesn't cause any torque. This is the one that causes the torque. And by including the sine theta in the formula, it's actually going to give us that number. It's going to give us that component. So you don't have to worry about breaking it down to components. Sometimes it might be easier to do that, but you don't have to do it. It's included in the formula. Okay? Questions there? Good there? Go.
So there's no torque because anything, none of the components for this thing can go through?
This one doesn't cause any torque, okay? But here, if we apply a force like this, right, this component will cause torque. It'll cause the nut to start, or the bolt to start spinning.
So just add it in.
Well, no, this, remember the formula looks like this, right? Tau is equal to F times D times sine of theta,
Oh.
okay? The F sine theta, right, gets you that side, and that's the one that causes the torque. Julie, go ahead.
So should you always use the angle above the force?
Technically, it really doesn't matter, because if you take, like, the sine of this angle, and then you take the sine of this angle, it's the same thing. Yeah.
Is there any time that you only have one component to use so much torque?
Yes, like if I did this, if I applied the force this way, does that make sense? What's the angle here? 90. What's the sine of 90? Okay, so that means that, right, in this case here, right, all of my force is going to apply torque. So if you're trying to spin something, that's really how you want to apply force. You want to apply it perpendicular to the object that you're trying to spin, because now all of your force is going to applying torque, causing that change in rotation. Okay, does that make sense?